And welcome to Activity 32. Today we are going to start talking about vectors and mainly their component form and magnitude. Now, a vector is a mathematical object that possesses both a magnitude, a length, and a direction that it is pointing at. They are fundamental in things like physics, engineering, computer graphics, and other fields. Our component form is going to show us the convenient way that's going to be able to show eventually that magnitude and direction as well as the movement of that vector. So that component form is represented with these brackets and a comma b, where a is showing the change in our horizontal component, how much you're moving left or right, and then b is the vertical component, how much you are moving up or down. And again, we kind of assume in this format that it would start at the origin and then point towards the point A comma B. Now, officially though, the movement of your vector, it doesn't have to start at the origin. It just starts at a tail, which is again its starting point, and then it moves towards the head, kind of the arrow portion of this. So that's, again, can be represented anywhere officially on our graph, but that will be pointing. And again, the movement, if it's positive, is going to be right for the A values, up for the B's, or negative would indicate left and down for the B's. So if we look at the examples given here, they are telling us, again, kind of given the picture, what we would need to do in order to write that. So again, you want to always start and think, okay, if I started at this tail, how much did I move to get towards the head? Well, in this case, I would have to move to the right 4 units and up 2 units. So my movement would be 4, 2, 4 right, up 2. Vector P, if we start at the tail, we would move left 4 and down 2. So -4, -2 would be the proper component form for vector P. All right, sometimes we are given, however, the coordinates, and what we would need to do is take the coordinates of the head and subtract away the coordinates of the tail each time in your corresponding x and x, y and y. So if we are starting at the tail and then we are moving to our head, again, you always want to think on these, your head coordinate minus your tail coordinate to show that movement. So we would take the x values of the head, so -1, and subtract away the x component. These will be our 2 a's, if you will, for the first part. And then we'll do the same thing with the y values to get b, the b value of the head minus the b value of the tail. So in this case, we would move to the left 3 and up 7, because remember, minus a negative really turns into addition. This would be our component form. And that makes sense, because if our point is starting at -1, 4 and moving to the right 2 and then, up from 2 to -1, you'd be going left, and then to go from -3 up to 4, you'd be moving up 7. Now in this next one, it's not specifically listing head versus tail, but if you're starting at a point, that's going to be your tail value. Your ending point, again, will be the direction that arrow is pointing in. That would be your head coordinate. And we would, again, take the value, the x value from the head minus the x value from the tail, y value from the head, y value from the tail, to get our final component form of 3, 3. So right 3 and up 3 on that one. Now, in order for our vectors to be equal, okay, we need them to have the exact same component form, right? They have to have the exact same horizontal and vertical movement, always the same signs matching on that. Again, they would have to be moving in the same direction. Essentially, they are parallel and point the same way. They would be the exact same length as well. So if we look at the example in 5, our vectors v and u equal. Well, if we think about the component form of vector u, it would be moving to the right 4 and up 1 to get from tail to the head. And then for vector v, we would be moving to the right 4 and up 1 to get from tail to head. So because their component form is the exact same, we would say, yes, these are equal. The component form for both is 4, 1. Now, in the second example, okay, while these arrows are the same length, they are not necessarily going to be equal, because we talked about actually these examples on the first page that vector Q is 4, 2, and then vector P, you went left 4 and down 2 to move from your tail to your head. Okay, so because these are not the exact same, right? They have to both be matching in signs. In this case, they are both wrong. Our direction is not equal this time. Again, length would be the same, just not the direction in which it's pointing. All right, speaking of the length, our length of a vector is called its magnitude. And so sometimes you will see that denoted either with a double bar or single bar around it. That's telling you you want the magnitude, aka the length. And essentially it is found by taking Pythagorean theorem, or the square root of a squared plus b squared in each of these. So for the first one, if we are looking for the magnitude of vector u, we would take the square root of a squared plus our b squared. So square root of 25. Our magnitude is just 5. On the next one, for the magnitude of vector v, again, we want to square our a values and b values, add them together. 4 plus 25 is 29. You could either leave that as an exact value. Sometimes it may be to your advantage to find the decimal approximation as well. In this case, that would be about 5.4. Usually we like the exact value though. List both. All right, last one is for you to try. Thanks everyone for watching. We will talk more about vectors in class.